So today we're going to focus on this target. I can use abbreviations to determine information that can be added or concluded from a balanced equation. Folks, this is the last target before things get nasty. Okay? This is the last, and this will set the stage for what we're going to learn next. So you must focus. And you have to believe me. I'm going to ask you to do something very weird halfway. And you're just going to have to trust me. Ask the juniors whether I am telling the truth or not. And those of the juniors who had me for a teacher will know that I'm right. All right? We'll see. Okay. Balanced equations can tell us certain things. A balanced equation can tell you whether something is exothermic or endothermic. How? Well, chemists can add the term energy, or just E, to the reactant side or the product side in order to denote whether something is exothermic or endothermic. What is the difference between exo and endo again? Can anyone tell me? Raise your hand. Danielle.
Exo is out and endo's in.
Okay. I was being a little more specific than that. Exothermic and endothermic. All right, yes?
Exothermic is when energy is released through chemical reaction, and endothermic is when energy is gained. It's more than that. It's almost like when energy is required in a chemical reaction in order for it to work. Okay? So, if you are placing the term or the letter E or the term energy in a reaction, where would you place it if you were dealing with an exothermic reaction? On the reactant side or the product side? Yeah. And in an endothermic reaction, because it's almost as if without it, the reaction will not occur, then we would place it on the reactant side. So, in an exothermic reaction, energy is released. You will find the term energy or the letter E on the product side. If you're dealing with an endothermic reaction, energy is going in, energy is required for the reaction to occur. It's almost as if it's one of the reactants. So you would find the term energy or the letter E on the left side. All right. Write a balanced equation for the reaction of hydrogen gas and oxygen gas to produce water and enough energy to provide propulsion for the space shuttle. Karan, go for it. Hydrogen gas. Is it one of your diatomics? Plus oxygen gas. O to the second. No. O2. O2. Resulting in water. Okay. Is there a clue as to whether this is exothermic or endothermic? What is that clue, Corrine? No, that really doesn't help you. You're trying to balance it. I'm just trying to find out where the letter E should go. Corrine produces water and unfortunately, you're going to have to put your English thinking caps on in order to decipher this. It's not that hard. In this case, the and was a sure giveaway, wasn't it? Okay. Let's balance it. How many H's? How many H's? Corrine, good job. How many O's? How many O's? Uh-oh. Fix it. Okay, she was shrewd enough to realize that by adding a 2 there in order to fix the O, she had just messed up the H's. So she had to go back. That is why it's so important to always go back and check. Because sometimes in your zeal to fix something, you may have just messed something up that you had already fixed. Write a balanced equation for the reaction of hydrogen peroxide decomposing when it is heated to form oxygen gas and water. Do you have a question? You want to try this one? Okay, hydrogen peroxide
I'm okay, so hydrogen
is,
is H. Well, it's a brother.
okay. It is a brother Huncliffe if it's by itself.
Okay.
Hydrogen peroxide is part of a compound here.
Not by itself, so it's
Charge,
+1.
peroxide,
O2 -2.
final formula.
So you have to do H2O2. And then
Yields,
when it's heated to form oxygen gas, so it's O2.
because O2 is by itself and it is one of the brother Huncliffes.
And then it's plus H2O.
Okay? Any clue as to whether this is an endothermic or an exothermic reaction? Okay, so it's almost as by implication, if it's not heated, then it won't work, right? Because it says when it is heated, which is implying that if it's not heated, nothing's going to happen. So, where would you expect to find the letter E? On the left side. For people who don't know left from right, that means on this side. Okay? All right. How many H's? How many H's? Good. How many O's? How many O's? Oh, yeah. And what's worse, this is an odd number of O's, right? So anytime, if you're going to try to make this, multiply this by another number, you're still going to have an odd number.
You could put 2 with the H2O.
Okay, that would even out this O, so now you have 4 O's.
Yeah, and then you could put 2 on the other side. And then it'd be even because it'd be 2 H, 4 H's on that side, 4 H's on that side.
Excellent. Good job.
No.
Nice. Phase notation is a simple way of describing whether a species, and a species is a word that we will use to describe both atoms and compounds and ions. It's just a very generic word. A species is a gas, we give it a G. A liquid, we give it an L. A solid, we give it an S. An aqueous, we give it an AC. AQ. Okay? Without this little notation, sometimes reactions that we think would work may or may not work. These notations let us know very important things. Okay? You will see. First of all, what is aqueous? What is aqueous? Aqueous solutions are usually ionic compounds, not always, but usually ionic compounds, which when you add it to water will dissolve in water. Now, some people think that dissolving is a chemical change. It's not. All you're doing is changing geography. The ions were together and are just simply spreading out. You get rid of the water, then the ions have no choice but to come back together. Why do ionic compounds do this? Well, ionic compounds are made up of positive and negative ions. And water has a positive and negative side. We'll find out that water is extremely polar. So what happens is, water picks it apart, separates it into the individual ions. Will completely surround the ions. But it won't actually react with the ions. It'll just pick it apart. Let me show you.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
So when something dissolves, that's really all that's going on. Water is literally just coming through and just picking it apart. Now what happens when water evaporates? Then they have no other choice than to go back together again to form crystals. So that tells you right there that you're dealing with a physical change, not a chemical change. Dissolving is a physical change. So, after a while, this is what you would see. Sodium surrounded by water molecules, all admiring sodium, telling it, "Ooh, you're so positive. We just love the way you're so positive." And over here, the hydrogens are going to the chlorine going, "Ooh, you're so green and negative and pig." Okay? So they're just whispering stuff like that to them. And the sodium ions and the chloride ions are just, they're just blushing and are being really flattered. So they're willing to follow water everywhere until water leaves them, in which case the sodium and the chloride get back together because they don't have any other choice. Okay? Now, do all ionic compounds do this?
No. Yes.
The answer is, truthfully, yes. But I'm going to lie to you, and you need to believe the lie from now on till April. And in April, I will admit to you that I have been lying to you all along. Okay? So I am lying to you. But this will be the last time I admit that I'm lying to you until April. Are you ready? Okay. No. Some ionic compounds do not dissolve in water. No, they don't. They do not dissolve in water. Okay? So, that is the problem here. How do you know whether an ionic compound will dissolve in water and not dissolve in water? Okay? You could get up here and, if you don't like music, some of you do not like music. Southmate here does not like music. She hates music. Okay? She will memorize his entire chart. What does this chart mean? Well, basically, nitrates, anything that's bonded to a nitrate is going to be soluble. What does that mean? That means it dissolves. Soluble means dissolvable. All alkali metal ions, when they're bonded to whatever, will dissolve. Chlorides, bromides, iodides, and throw in fluorides there, will dissolve, except if they are bonded to silver, mercury 1, or lead 2. So they will all dissolve except for mercury 1, lead 2, or silver. Yes?
Should I write this down?
No. Sulfates are all going to dissolve. Well, not all. How about barium, lead 2, and calcium, or strontium? The ones that don't dissolve at all, wink, wink, are the sulfides, carbonates, phosphates, and hydroxides. Unless, of course, they're bonded to an alkali metal ion or ammonium or calcium or barium. Okay? Now, that's really boring. It's a whole lot better just to learn this song.
This song was written by this chemistry teacher by the name of Michael Offit. I have an email from him telling me that it is okay for me to send you this MP3, which I already have. It's on a Skyward message last Friday. I have now given you the lyrics to the song. If I were you, I would write down some of the notes that I wrote on the lyrics in order to help you understand the lyrics a little bit better. And, oh my friends, ask the juniors. They will confirm that you need to memorize this. Or else, well, good chunks of it. Or else, in a week from now, you'll look at me and go, well, how do you know that sodium chloride dissolves? And I'll look at you and sing the song to you. Alkali metal ions are really swell. Assume their compounds are always soluble. Next week, I will sweetly sing that song to you. In 3 weeks, somebody's going to ask me, Mr. Moreno, how do you know that sodium chloride dissolves? And I'm going to look at you, and my eye's going to twitch. And I'm going to say something like this. Alkaline metal ions are really swell. Assume their compounds are always soluble. And then 6 weeks from now, near the end of the 9 weeks, somebody, I promise you, this will happen. It always happens. Somebody will raise their hand and ask, how do you know that sodium chloride is soluble? At that point, my face will contort into rage, and I will start growling. Alkali metal ions are really swell. Assume their compounds are... And then I'll stop, and everyone will scream, always soluble. This will happen. I know this, because it always happens. Okay? So, let's start the song.
Solubility rules. Solubility rules, they're really great. They help predict precipitate.
Stop. What's a precipitate? A precipitate is a solid. It's crystals. You see, what we're going to play around with is this situation where you have sodium carbonate. Sodium carbonate dissolves in water, so you'll basically have a bunch of ions dissolved in water. And then you have a jar or beaker of calcium chloride, where you have calcium ions and chloride ions, and they're following after water. So what happens if you pour them into each other? Then what's going to happen is that the calcium from one beaker is going to meet up with the carbonate from another, and they're going to come together and form a solid. To us, it looks like these solids are raining down to the bottom of the beaker. And that's how they came up with the term precipitate. Precipitation. Raining, snowing. Okay, because it kind of looks like it's raining down. It's not. But it looks like it's raining down. So that's why they call it a precipitate. Yes?
Is this ours to like?
Yes. And the song is, according to Michael Offit, yours to put on your iPod or your MP3 player. Okay, just, he doesn't want you to sell it to anybody else. Yes? What? AQ. AQ means dissolved in water. All right.
What a marvelous tool. Solubility rules. Alkali metal ions are really swell. Assume their compounds are always soluble.
All right, so alkali metal ions, sodium, lithium, potassium, rubidium, but we won't play around with rubidium very much. Assume their folks, if they meet up with water, they will always follow after water. They'll always dissolve, period. That's what always means. Sorry, it's been many years. I've been worn down. Okay, people sometimes don't understand the word always. Those ions are hardly precipitators. In reactions, they're usually spectators. A spectator is somebody that just kind of looks on and doesn't do anything. That's what a spectator ion is. Just
Bad grammar.
they just watch.
Yeah, it should be they are.
Fine.
Those ions are hardly precipitators. In reactions, they're usually spectators. And that positive one ion NH4, its compounds are soluble for sure. And that negative one ion NO3, nitrates are as soluble as can be. Solubility rule.
Okay, so what does that mean? That means if you see anything with ammonium in it, it's it's aqueous, it dissolves. Anything with nitrate, potassium nitrate. Does potassium nitrate dissolve, Mr. Moreno? Yes. How about copper nitrate? Yes. How about aluminum nitrate? Yes. How about sodium nitrate? Yes. How about anything nitrate? Yes, 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 yes. Sorry. All nitrates dissolve.
And the other was ammonium.
Ammonium, anything with ammonium dissolves.
Rules, they're really great. They help predict precipitates. What a marvelous tool. Solubility rules. Of course, we know one thing is always true. There are always exceptions to the rules. Sulfates are soluble, it's said, except with barium, strontium, and lead.
Okay, so now we've left behind the ones that are always soluble. Here are sulfates. Sulfates are mostly soluble. Almost everything dissolves when it has sulfate in it, except for barium, strontium, and lead 2. And I always like to add the 2 there because it could be lead 4. Lead 2. There's also, I think, calcium does not dissolve. That's what the few others means. You'll encounter those in AP chemistry, and Eddie will teach you. All right? So, most sulfates are soluble except for calcium, strontium, and lead 2.
And a few others. Chlorides, bromides, and iodides are soluble.
Okay, most halides are soluble. Period. End of story. Except for 3.
But there are some secrets, well, I'm gonna tell. Working in the lab, it's plain to see. They're insoluble with silver, lead, and mercury.
All right, so most halides are soluble except when they're bonded to silver, lead 2, or mercury 1. And this is why you have to learn the song. This is why things get a little complicated.
Solubility rules, they're really great. They help predict precipitates. What a marvelous tool. Solubility rules.
Okay, let's get to the ones that normally don't. Let's get it all. These are the ones that normally insoluble. Means they don't dissolve.
Many ions make precipitates, including phosphates, sulfide, and carbonate,
And hydroxide.
except when paired with ammonium or alkali metal ions. Hey, it's hard to make this simple.
But I'm trying. Okay, so phosphates, sulfides, carbonates, and hydroxides, by and large, will precipitate. They are not going to dissolve in water. Except, of course, if these guys are bonded to ammonium or an alkali metal ion.
But I'm trying, so consider all the possibilities.
Really, the song at this point continues on, but as far as the rules are concerned, it's no longer important. All right, let's sing it from the top. Go.
Okay, for
Did you add hydroxides to it?
Sodium.
Okay.
Let me write that. And then it says, so they aren't soluble?
They're not good. They're going to be solids.
If they're paired with?
Unless they're paired with alkali or ammonium, in which case they are AQ.
Okay.
So all of those are typically solid unless they are paired with alkali and ammonium, and then they are AQ. You ready?
Solubility rules, they're really great. They help predict precipitates. What a marvelous tool. Solubility rules. Alkali metal ions are really swell. Assume their compounds are always soluble. Those ions are hardly precipitators. In reactions, they're usually spectators. And that positive one ion NH4, its compounds are soluble for sure. And that negative one ion NO3, nitrates are as soluble as can be. Solubility rules, they're really great. They help predict precipitates. What a marvelous tool. Solubility rules. Of course we know one thing is always true. There are always exceptions to the rules. Sulfates are soluble, it's said, except with barium, strontium, and lead, and a few others. Chlorides, bromides, and iodides are soluble. But there are some secrets, well, I'm gonna tell. Working in the lab, it's plain to see. They're insoluble with silver, lead, and mercury. Solubility rules, they're really great. They help predict precipitates. What a marvelous tool. Solubility rules. Ions make precipitates, including phosphates, sulfide, and carbonate,
And hydroxide.
except when paired with ammonium or alkali metal ions. Hey, it's hard to make this simple, but I'm trying. So consider all the possibilities and use the rules to guess the solubilities. The most important thing that you must keep straight: the insoluble combinations precipitate. Solubility rules, they're really great. They help predict precipitates.
And it continues on there.
Solubility rules.
All right, so chlorine gas, GLS or AC. G, and what gives that away is gas. Water, L. Steam, G. Ice. Solid sodium chloride. How about sodium chloride if it's dissolved in water? AC. AC. Bromine.
L, right? L.
Bromine is your only non-metallic liquid. Iodine. Iodine is below bromine, and because bromine's a liquid, iodine must be a solid. I showed you iodine when we did the volcano demonstration. Mercury. Mercury is your only metallic liquid. Nitric acid. Get this one. Write it down. All acids are AC. All acids are Ac. All acids are ac. Carbon dioxide.
Gas. E.
All right. Balance the following. Okay. So, Abby, hydrochloric acid formula.
That would be HCl.
Phase. Okay. All acids are aqueous. And what this means is that this is now a watery solution. That means you can have other acs. Plus zinc. Is it one of your diatomics? Phase. All metals are solid except for mercury. To form zinc chloride. Phase. Chloride is a halide. Chlorides, bromides, iodides are soluble, but there's a secret I'm going to tell. Working in the lab, it's plain to see they're insoluble with silver, lead 2, and mercury 1. So it's zinc, any one of those exceptions. Okay, so it's, and that is why we learned the song. Plus hydrogen gas. Is that one of your diatomics?
Yes, so it's H2 and then CH.
Very good. How many H's? How many H's? Fix it.
2 in front of it.
How many CLs?
You got 1. You got 2 over there.
How many
Right.
CLs?
You got 2.
How many CLs? How many ZNs?
1.
How many ZNs?
1.
Good job. Oh, any clue as to whether this is exothermic or endothermic? How do you know? What's your clue?
With an energy accepted, it says with a release.
Very good.
Also turns into a gas that doesn't solid.
Mr. Moreno,
Yes,
why do you have to put like the phase notation in there?
because as we'll find out, sometimes reactions may or may not occur, depends on what phase they're in. Water will react. How about Lauren? Water.
H2O.
Phase. Plus sodium metal.
Na.
Phase. Is sodium one of your diatomics?
Yes. No.
Which one is it? Yes or no?
No.
Okay. Phase.
Solid.
All metals are solid except for to form sodium hydroxide.
Na. OH.
All right. Is there any mention of water in this? Because all ionic compounds are solid unless there's water involved. Is there water involved?
Yeah.
Okay, so now we need to go to the song. Is sodium hydroxide ac or solid? Sodium is an alkali. Alkali metal ions are really swell. Assume their compounds are always soluble. Notice how sweetly I sang that? I'm not going to sing it very long, sweetly. So, all sodiums, all potassiums, all lithiums are soluble, ac. And hydrogen. Is that one of your diatomics?
Yes. H2.
Phase.
Yeah. Or two.
All right. How many H's?
2.
How many H's?
2.
And?
Oh, 3. Well, 3 total.
Okay, so how are we going to do this?
Put a 2 in front of log. Yeah, put a 2 there.
Here?
Yeah. And put a 2 on the left. No, yeah, on the right. Right.
Okay, so that's 2 H's and 2 more is 4. 2 times 2 is 4. Okay, good. Is everything else balanced?
No, put a 2 in front of the NA.
All right, any clue as to whether this is endothermic or exothermic? Yes?
It's exothermic.
How do you know?
It's releasing
So where do you put the E?
on the right side.
All right. So what I want you to do is 8.1B for homework.